One other thing that we'll look at for bone growth is how certain hormones help play a significant role in bone growth. For example, growth hormone. Now, when you get to 169, you'll study the endocrine system, and you'll go through many different hormones, including growth hormone. But just a few examples here of some of the hormones that have a direct impact on bone formation and bone growth. Growth hormone is a hormone that comes from the pituitary gland, which is kind of located at the base of the brain. And this helps to build up cartilage and the osteoblasts, helping the bone matrix to form and grow. Thyroid hormone is also important for growth of any kind of tissue. The thyroid gland produces thyroid hormones. You may have heard about T3 and T4. These are thyroid hormones that are involved in metabolism, and they help to provide the energy needed for the growth of tissues, including bone tissue. Then also your sex hormones or your reproductive hormones, including estrogen and testosterone, these also stimulate growth. These become active or secreted at puberty, and they help to kind of strengthen the bones. They help to add some calcium to the bones, and that helps in how strong the bones are. They also trigger, though, a cessation of growth or a slowing down of the growth, because that epiphyseal plate that you find in those long bones actually begins to close. That the cartilage that we talked about inside of the epiphyseal plate, that begins to harden or ossify after these hormones are released, and so that slows down and eventually stops your growing, the length of the bones from growing. Now, in the next section, we'll look at something called bone remodeling and bone repair. If you've ever broken a bone, then you've gone through some type of bone repair. And bone remodeling is actually a process that everybody goes through. It's a continual type process of where your bones are basically, like it says, that they're kind of remodeled. And so you have old bone, old matrix that gets broken down, and that's called bone resorption. It actually gets broken down, and then it's replaced by new bone. New bone deposition replaces where you've removed some of the old matrix and the old bone cells. And this happens for a variety of reasons. It helps in the process of balancing your calcium levels. We'll talk about some hormones in just a minute that help to balance calcium levels in the blood. Remember, your bones are a storage site for ions like calcium. And so when you need that extra calcium in the blood, then you have this bone remodeling taking place to try to get some of that calcium out of the bone matrix and putting it back into the blood. And then the reverse happens. When you have too much calcium in the blood, or you need to restore some of that calcium back into the bones, you have this bone remodeling process to help to do that. Another time you'll see bone remodeling is anytime you're replacing that primary bone or that woven bone we talked about earlier with secondary bone or the lamellar bone. That process of making that more mature type bone, that's part of bone remodeling. Anytime you break a bone or injure bone tissue, then you have a bone repair process, and that requires bone remodeling. Sometimes there's replacement of older brittle type bones. And then also adaptation to tension and stress. Physical stress, mechanical stress on a bone, and tension on a bone stimulates those osteoblasts to work a little harder and to deposit more bone matrix. This is why it's critical for people to get exercise that gives you a type of tension and mechanical stress. Moving around stimulates those osteoblasts to work faster and work harder to kind of strengthen the bones, put that calcium into that bone matrix to give you stronger bones. And so the process of bone remodeling kind of can be seen here in this little figure here. It mainly involves those two main types of cells, the osteoblast and the osteocytes, and really the osteoclasts are part of this as well. And so here in the little diagram, you see some bone here and you see some osteoblast here. Remember, the osteoblasts are in charge of depositing the bone matrix, making the bone matrix to help strengthen the bone. You see some mature bone cells, the osteocytes, and then you see some osteoclasts, and their job is to go through and start breaking down some of that bone, and that's the process of bone resorption. And like I mentioned earlier, here's a few things about that stress or tension. Mechanical stress is what we're talking about, and that helps to increase the osteoblast activity. That in turn causes your osteoblasts to speed up. That causes more bone matrix to form, and that helps in having stronger bones or having higher bone density. If anything decreases mechanical stress, maybe you've got an injury and you can't move, that leg or that arm, that bone, or you've got a long-term disease and you're immobilized for a long period of time, that eventually causes a decrease in your osteoblast activity. However, your osteoclasts actually remain the same. They continue to break down some of that bone matrix, and so it ends up you end up having weaker, or you lose some of that bone density or some of that bone mass. So it's very important to have exercise, movement for the body, and that helps to strengthen the bones. Now, there are a few other factors here we'll kind of mention that help to influence this process of bone remodeling. You got a lot of different things here. Hormones play a big key in a lot of different things, including the bone growth and even the bone deposition. Actually, testosterone helps in this process, and that's mainly produced by males in the testes, but actually it's produced also in the adrenal gland for both males and females. So females have a small amount of testosterone produced there, and that does help in the process of the calcium, adding that calcium to the matrix. And then estrogen, that seems to slow down the osteoclast, and so that again helps to with bone deposition, because if you slow down what the osteoclasts are doing, that allows the osteoblast to continue working and building up that bone. Age is a factor, and so many things slow down as we get older, and so protein synthesis slows down. And remember, you do have proteins in your bones because you've got collagen fibers as part of that organic portion of the bones, and so that tends to slow down. Calcium, that's very important, of course, because that's one of the raw materials for the bone matrix. And then you have several vitamins that are here that are important. Vitamin D, that's directly connected to calcium levels, and so vitamin D is required to help you reabsorb calcium in your system. And so if you don't have enough vitamin D, if you're vitamin D deficient, of course you get vitamin D we talked about from UV radiation, kind of helps produce that vitamin in the skin, in the body. And of course you can have vitamin D supplements, and it's in some of the foods like milk and dairy products. And so that vitamin D is important. If you don't have enough vitamin D, then the calcium that you're ingesting is basically just wasted. It just comes out through the digestive tract. And so it's very important to help maintain your calcium balance. Vitamin K, this is another vitamin that you sometimes produce a small amount of, but it does seem to help in the function of some of those bone osteoblasts. And then vitamin C is very important. Of course, protein in your diet is very important, and that's because they help in the synthesis or the production of protein fibers, the collagen fibers that make up the bone. Now, we mentioned calcium. Of course, that's very critical for the bone density, but it's also very critical for other systems in the body. You need calcium, of course, for bones, but you also need calcium for your muscles to work correctly, for your nervous system to work correctly, and we'll see that as we get into some of those chapters a little later on about muscle physiology, how your muscles function down at a cellular level, and how your nervous system function. They both require calcium. And so calcium is an ion. It's a charged ion that allows for that the body really has to maintain in a certain concentration inside the blood and inside the body. And so, of course, that's being regulated by those osteoblasts and osteoclasts. So I have that up here for you again, because osteoblasts are building the matrix. They're taking calcium from the blood and they're causing it to go into the bone. Osteoclasts are breaking down the matrix, and so that's causing calcium to leave the bone to go into the bloodstream. Now, this whole process is being regulated by two main hormones, two other hormones we haven't talked about yet, parathyroid hormone and calcitonin. You have a gland called a parathyroid gland that produces parathyroid hormone, and its job is to speed up, kind of increase what the osteoclasts are doing. And so by speeding up the osteoclast, that allows for more bone resorption, um, breaking down some of that bone matrix, and that causes more calcium to leave the bone and go inside of the blood. So it increases the blood calcium levels. Calcitonin is an antagonist, or the opposite basically, of parathyroid hormone. First of all, calcitonin is produced by your thyroid gland, and it helps to lower your blood calcium levels, and it does this by slowing down your osteoclast. If you slow down the osteoclast, that means the osteoblasts continue to work faster, and they continue to work harder to kind of get the blood calcium levels, lower the blood calcium in the blood, and send that calcium over to the bones. So that's the job of calcitonin. These are basically working, really working together, opposite of each other, to help to control your amount of calcium, try to balance the amount of calcium that's in the blood. Of course, that's a type of homeostasis. Now, want to look at bone repair, and there's a few things here, the few steps that are involved in bone repair. Let's say, for example, there's a damage or an injury to a bone, or broken bone, or fracture. These are some of the main steps that are involved in repairing that. First of all, you can kind of see in the diagram, here's a bone that's been broken, and you have what's called a hematoma. The definition for that is up here: localized mass of blood confined within an organ or cavity. In other words, you're bleeding inside of a cavity. It's not, it's being contained here, but if you break a bone, there's blood vessels supplying blood flow to that bone, and so it begins to bleed. Just like you cut your skin, that bone is going to bleed, but most likely it's going to be contained with inside of the bone, and so that's referred to as a hematoma, and will eventually begin to clot. Just like you have a blood clot that forms if you cut yourself, and so it's going to form a clot at the site of the breakage there. That clot hopefully stops the blood from escaping, but it doesn't necessarily fix the problem. It's a temporary patch, right? And so the second thing that forms is what's called a soft callus. And this is where tissue starts to begin the process of reconnecting those two ends of the bone. And so you have cells that start to form and grow into the broken, into this damaged area. Blood vessels start to grow into the clot area, and they send in several different cells that are very important. Macrophages, these are specialized types of white blood cells that go through phagocytosis, and they have the ability to kind of engulf and eat up, maybe there's some broken cells around that area, or dead cells, or even maybe some infection that has started in that area. So macrophages are part of your immune system, try to help clean up any type of cell debris or problem that's in that area. Osteoclast, they're in charge of breaking down bone matrix, but they can also get rid of some of that old bone tissue. If the old bone tissue is damaged and perhaps dead bone tissue, then those osteoclasts can go through and kind of break those up. And then the fibroblast, notice again the words here. Blast means it's building, and fibro just refers to fibers, and so a fibroblast is building protein fibers. If you've damaged a bone, then you've damaged some bone cells, but you've also damaged the protein fibers, the collagen fibers that make up that bone, and so you got to replace those. So a fibroblast is a type of cell that's going to help you go through and build up the protein fibers. That soft callus is also a temporary fix again, and so it's going to be replaced by what's called a hard callus, or actually true bone. But remember, that first bone that comes on the scene is that woven type bone, or the spongy type bone. And so here you kind of have that callus region, this collar, kind of forms a collar around the bone, and it starts to harden. It starts in the process of ossification. That's because you got those osteoblasts starting to build up that bone matrix again. But again, it's going to be that primary type bone, or that woven type bone, until eventually the remodeling process comes in, and that kind of is what's going to replace any of that woven or primary or spongy bone with the more mature and more dense compact bone. And so that kind of finishes the problem to get that secondary bone in place, is bone remodeling. Now, the last thing we'll kind of look at are some terms associated with bone injuries or bone fractures. Anytime you break a bone, it's what's referred to as a bone fracture. And so really they're categorized into two main categories: open or closed, or sometimes you see the terms compound for open or simple for closed. If the bone breaks and it actually penetrates the skin, then that's an opened fracture or a compound fracture. And then if you have a broken bone but it doesn't penetrate the skin or perforate the skin, then it's a closed fracture or a simple fracture. And your book kind of gives you a table. This is table 6.1, maybe kind of hard to see here in the video, but take a look at this sometime. It gives you examples of different types of fractures, and you can kind of see by the diagrams and by the scans, the x-rays, what these would look like. For example, a spiral fracture, you can see that the bone is broken here, and you see that you have kind of a twisting action that has turned the bone and kind of has that little spiral look to it. You can have compression type fractures where, especially like in the vertebral column, you have the vertebrae here, and we're going to be talking about the different bones very soon, the skeletal anatomy, but it actually compresses and crushes a vertebrae. And I've got one other diagram you can kind of look at that has some examples here. You can see terms like complete type of fracture. It goes completely through the bone. Sometimes you have an incomplete fracture where only a portion of the bone is broken, but it doesn't go all the way through the bone. You have something called a comminuted fracture where you've got, you've kind of broken up the bone into fragments. It's kind of the main thing here. You have an impacted fragment. That's what I have a definition up there for. Impacted fracture where part of a bone is impacted into, driven into another portion of it. In this case, you see the femur here, and the femur, the pelvic joint here, and the head of the femur has kind of been kind of compressed impacted into itself there. And you see a picture again of the spiral fracture.